Hi chemistry students, this is Mrs. Miller. Today we're going to be talking about specific heat. We're going to be going through some calculations and just going over some basics about what specific heat is, how it's different for different substances, and so on. If you haven't already, you're probably going to want the specific heat capacity practice problems either on your iPad, printed out, or have that copied onto a piece of note paper, because today when we go through our video, we're going to be doing number 1 and number 5 from those together so that you won't have as many to do on your own. So if you haven't done that, do that and then come back to this video. We're going to start by talking a little bit about energy and change. So first we need to identify what energy actually is. And energy is the capacity to do some kind of work, such as moving an object, forming a new compound, which is what we really talk a lot about in chemistry, or generating some sort of light. There are other things that energy could be. Usually I just say the capacity to do work. So energy is always involved when there is a change in matter, and we're going to be talking about different changes in matter today in the form of heat and temperature. So we see some examples of energy here. Let's say I had a little ball down here. I could draw that for you guys. So we have this little ball on the bottom. If we were to take this ball and now we kick it so it goes over this garbage can, that would be a form of energy, and that energy would be kinetic energy, but that's not the energy we're going to look at today. Another form of energy that we can see is right here with this candle. We see light energy because we see the candle has lit up for us. Again, that's not the type of energy we're doing or we're working with today, but both of those are different types of energy that may involve some heat that we're going to be talking about, like this candle. If you put your hand over the top of the candle, you'd feel that as heat. What we really want to look at with specific heat capacity is we want to follow where this energy is going. So we're going to talk about two different types of reactions essentially, and we're going to see that some types of reactions are going to have energy being added into the system, while others are going to release it from that system into the surroundings. So essentially we're talking about endothermic or exothermic reactions where one feels warm or one feels cold. And they feel that way because of the direction that heat is moving, into it or out of it. So we can look here, and it says energy is added to a pot of water to cause it to boil in a process called evaporation. So the water has to absorb energy, and as it absorbs that energy, it's going to allow it to go from one state to another. The explosion that occurs between hydrogen and oxygen, like we did with our rocket lab, is going to create water, causing a release of energy. So that's why we were able to shoot those little rockets across. There was a release of energy. Some of you may even felt like those little rockets felt a little bit hot because heat was coming out. So that would be an exothermic reaction. One thing we want to be able to do is to understand how the energy is being transferred and really where is that energy being transferred, from where to where. So oftentimes we want to keep track of this by talking about two terms. One will be the substance and one will be the surroundings. So when we talk about a substance, that's going to be the component that is being studied at the time. For example, it might be whatever we put inside of the Erlenmeyer flask. It might be inside of a test tube. It might be inside of a burette or any other piece of glassware that we might use in the lab. And it's just like the mixture of things that we're going to put together there. The surroundings are literally everything else outside of that substance. Sometimes we call that the system. So the surroundings would be the air on the inside of the flask or outside of the flask itself. Anything that is not actively involved in that reaction is going to be called the surroundings. So we just talked about how energy is transferred from one object to another. The substance, the surroundings, might go in one direction, in, or might go out. But what we're really talking about here is heat energy. So heat energy is the energy that's transferred between two objects that are different temperatures from one another. The cool thing about heat is it always moves in the same direction. It always moves from the warm object to the cooler object. For example, when we place ice cubes that are in water, the heat energy is going to go from the water into the ice cubes, and that's going to start the ice cubes to melt. You can also test this, so I'm sure many of us have had this happen, where you don't think that a piece of metal is hot, and you go and you grab that. Maybe it's a pot on the stove. So what happens is as soon as you grab that, your hand is cooler than the hot metal is. So heat energy moves from that pot handle into your hand, and you notice that pretty quickly, which is why you go, ah, and then you drop that. So that is where heat is transferring from the warm object to the cool object. We can have different reaction types based on which direction the heat is going, into a substance or out of the substance. So we know that energy as heat can be absorbed or released. So if I look at two examples, one is we can have energy as heat be released when there is an explosion that happens. So this is an example of an exothermic reaction. Another really good example is think about a bonfire. So we're burning that wood, everyone sits around that bonfire, and you feel that energy as heat. So the bonfire is a great example of an exothermic reaction. On the opposite end of that, we have something like a chemical cold pack. Heat moves from the outside to the inside, and it leaves the surroundings feeling colder. So this would be an example of an endothermic reaction. I'm sure we have all had an instance where you needed an ice pack at some point where that ice pack is really cool. You put it on your skin, which is warmer, so the heat is going to move from your skin and it's going to go into that ice pack. So same thing, like if you put ice on something, your arm is warmer than the ice that you're putting on there, so your heat moves from you into that system or in there, so that's endothermic. Endothermic feels cold, exothermic feels warm. One thing I don't want you guys to confuse is heat and temperature. Heat and temperature are two very different things. Heat is where we're looking at the energy. Temperature, or we're actually looking at particle motion. So temperature is going to indicate how hot or how cold something is. So if it's really, really cold, you have a low temperature. If it's really, really hot, you have a high temperature. But that is not indicating the heat of that particular object. Scientists are going to define temperature as the measurement of the average kinetic energy or the average movement, random motion of particles in the substance. So when you have something that is cold, you're describing its temperature, like ice, those particles aren't moving very quickly. So what happens when we get up to steam, that steam is going to be hot because those particles are moving faster. It's the transfer of that energy as heat that can be measured by calculating the changes in temperature. So we'll talk about kind of a little bit more about the differences between the two in a sec. So you guys have seen a heating curve like this already. We start down here with our solid, and this would be a low temperature. And as we move up to liquid, it's obviously getting warmer. And when we get to vapor, that's going to be a high temperature. So what you need to know, though, is we're going to be doing something a little bit interesting on here. You can see temperature on this scale. So as we go up, it's getting hotter. So low up to the high. That's why our solid is low, vapor is high. But here's the interesting part, the energy added as heat. So heat is increasing as we go, but you're going to see a few little areas where that stops or it looks like it's flat. So even though we're increasing the heat, the temperature is not changing. And that would be those two processes where we see either the melting or the freezing point, and then where we see evaporation or condensation depending on those directions. So we can still see that heat increases, but in certain points that temperature doesn't. So those two are independent of one another. Heat is that transfer of energy, temperature is the particle motion. What you need to know is that every substance needs a different amount of heat added to increase its temperature. So some things are going to need more heat to get warmer, others need just a little bit of heat to get warm. So it's the relationship between energy transferred as heat to a substance and the temperature change that we call specific heat capacity. So what is specific heat capacity? Well, we go with this crazy formal definition, which I'll read you. So the specific heat capacity of a substance is the quantity of energy as heat that must be transferred to raise the temperature of exactly 1 gram of a substance by 1 Kelvin. You're Probably thinking right now, what in the heck does that mean? Luckily, I've simplified that for you. So, essentially, specific heat capacity tells us how easy or how difficult it is to change the temperature of a specific substance. So we're going to talk about a few examples on the next slide. If you look at all the substances that are around you in whatever room you're in right now, my guess is there's a ton of different substances, which also is going to lead me to believe that there are quite a few different specific heat capacities represented in your room. So first, let's talk a little bit about metals. Metals are really common. So let's say I'm in a kitchen right now and I grab onto the metal sink. I'm probably going to notice that that metal sink feels really cool overall. But if I turn on the hot water, within a few seconds, now it's going to feel really, really warm. So the reason why that happens is because metals tend to have low specific heat capacities, meaning it's really easy to change their temperatures. So when I look at my pots and my pans, they heat up quickly. That's why you can burn yourself really, really quickly. You don't want to grab those handles, but they also cool down really quickly. Aluminum foil, phenomenal at this. Super low specific heat capacity. It can be in the oven for a really long time. It's super warm right when you take it out, but it'll cool off really, really quickly. On the other hand, we have other substances like water. Water has an extremely high specific heat capacity. It's really difficult to change the temperature of that water. So let's say now we're in the middle of summer. Wouldn't that be awesome? And we all want to go swimming. So what we do is we go out to a lake and we all jump in the lake. It's the beginning of May. We're like, oh, it's been warm out for a while. This water's going to be great. Woo, it is not going to be great. It is going to be really, really cold. That's because the sun hasn't hit that enough to warm it up. Now you go and you jump in that same lake in September, and even though it's starting maybe to cool off a little bit, it's had all summer to warm up. So now it feels warm longer. It's because it's very, very difficult to change that temperature. So in your house, maybe you go up to something like I have a bookcase next to me. If I put my hand on the bookcase that's made of wood, I'm going to notice that it doesn't feel nearly as cold as that sink did because wood is going to have a higher specific heat capacity than the metals. There is an equation that goes along with specific heat capacity, and what we're going to see on the bottom here, oops, didn't want to do that, what we're going to see is that Q, which is heat, or sometimes it's called enthalpy, so that's a good thing to know, heat or enthalpy, just meaning the heat going in, equals C, which is specific heat, M, mass, and delta T, which is a change in temperature. So, a couple things about the units. What we're going to see here is the SI unit for energy or enthalpy is going to be joule, so that is a capital J. In the English system, sometimes we refer to that as calories, like the calories that we're going to see on like a nutrition label. Similar, very, very similar. So the energy transfer can be expressed as Q or capital Q or lowercase q. Again, sometimes we call that enthalpy. And then the specific heat capacity, or C, is going to be expressed in joules per gram Celsius, or J per G times degree Celsius. So we'll keep working with this equation, but I want to go through a few questions with you guys.